Hey everyone, and welcome back to the channel. Today, let's break down the NISAR, NASA-ISRO Synthetic Aperture Radar mission, a collaboration between NASA, the US Space Agency, and ISRO, the Indian Space Agency, in a way that's easy to grasp. NISAR represents a landmark collaboration between NASA and ISRO, designed to provide an unprecedented view of Earth's dynamic surface. This joint Earth-observing mission aims to make global measurements of the causes and consequences of land surface changes, focusing on areas like ecosystem disturbances, ice sheet collapse, and natural hazards. NISAR's unique capability lies in its use of dual-frequency radar, allowing it to observe subtle changes with remarkable precision. This detailed observation is crucial for understanding key impacts of climate change and advancing our knowledge of natural hazards. The mission's data will be invaluable for a wide range of scientific studies and practical applications, from monitoring deforestation to assessing earthquake risks. The genesis of NISAR can be traced back to the scientific community's long-standing desire for a dedicated spaceborne radar mission. The National Research Council's Decadal Survey, which outlines priorities for NASA's Earth Science Program, NASA Control Station, consistently highlighted the need for improved observations of Earth's surface deformation, ecosystem structure, and ice dynamics. These needs converged in the DESD, deformation, ecosystem structure, and dynamics of ice, mission concept, which aimed to address these critical areas. However, realizing such an ambitious mission required significant resources and technological advancements. The partnership between NASA and ISRO proved to be a turning point. Recognizing the complementary strengths of both agencies, discussions began regarding a joint radar mission. ISRO's interest in applying radar technology to address specific challenges within India, such as agricultural monitoring, disaster assessment, and Himalayan glacier studies, aligned perfectly with NASA's broader scientific objectives. The collaboration allowed for the development of a more comprehensive and capable mission than either agency could have undertaken independently. The historical context of radar remote sensing is also important. NASA launched CSAT, the first civilian SAR satellite, in 1978. Although its operational life was short, CSAT demonstrated the immense potential of radar for Earth observation. It paved the way for subsequent radar missions and inspired the development of spaceborne SAR systems worldwide. However, launching another free-flying scientific SAR mission in the US proved challenging until the NISAR partnership emerged. The collaboration between NASA and ISRO brought together decades of expertise in space technology and Earth science. NASA contributed its expertise in L-band radar technology, while ISRO provided the spacecraft bus, S-band radar, and launch capabilities. This synergistic partnership allowed for the development of a dual-frequency radar system, significantly enhancing the mission's scientific potential. The open data policy adopted for NISAR further underscores its commitment to advancing scientific knowledge and benefiting society as a whole. The mission's development has involved extensive collaboration between scientists and engineers from both agencies, ensuring that the mission meets the scientific requirements and delivers high-quality data. The background of NISAR is rooted in the scientific community's need for advanced Earth observation capabilities, the complementary strengths of NASA and ISRO, and the historical context of radar remote sensing. The NISAR spacecraft is a sophisticated platform designed to house and operate the mission's complex instrumentation. ISRO is responsible for providing the spacecraft bus, which includes the structure, power systems, thermal control, attitude control, and other essential subsystems. The spacecraft is designed to operate in a sun-synchronous orbit, allowing it to observe the same areas of Earth at the same local time each day. This consistent observation geometry is crucial for detecting subtle changes in the Earth's surface over time. The spacecraft is designed for a nominal mission life of 3 years, with the potential for extended operation. It is equipped with redundant systems to ensure reliability and maximize data collection. The spacecraft's attitude control system is highly precise, ensuring that the radar instruments are pointed accurately at the Earth's surface. This precision is essential for acquiring high-quality radar data. The spacecraft also houses the mission's high-rate communication subsystem, which is provided by NASA. This subsystem is responsible for transmitting the large volumes of data collected by the radar instruments back to Earth. The spacecraft's power system is designed to provide sufficient power for the operation of the radar instruments and other onboard systems. The thermal control system maintains the spacecraft's temperature within acceptable limits, ensuring the proper functioning of all components. The spacecraft's design has undergone rigorous testing to ensure that it can withstand the harsh conditions of space and operate reliably throughout its mission life. The spacecraft's design has been carefully optimized to meet the mission's scientific requirements and ensure the successful collection of valuable Earth observation data. The integration of NASA-provided components with the ISRO-provided spacecraft bus has been a complex but successful undertaking, demonstrating the effectiveness of international collaboration in space exploration. ISRO is responsible for launching the NISAR spacecraft. The launch vehicle and associated launch services are provided by ISRO. The launch is a critical milestone for the mission, marking the beginning of its operational phase. The launch vehicle will propel the spacecraft into its designated orbit, where it will begin its Earth observation activities. The launch process involves careful planning and coordination to ensure a successful outcome. The launch vehicle is rigorously tested to ensure its reliability and performance. The launch trajectory is carefully calculated to ensure that the spacecraft is placed into the correct orbit. The launch team consists of experienced engineers and technicians who oversee all aspects of the launch process. The launch is a culmination of years of preparation and represents a significant achievement for both NASA and ISRO. The selection of the launch vehicle is based on factors such as its payload capacity, reliability, and cost-effectiveness. The launch site is chosen based on factors such as its geographical location and infrastructure. The launch window is determined based on factors such as the spacecraft's orbital requirements and weather conditions. The launch is a highly anticipated event, marking the beginning of a new era in Earth observation. The successful launch of NISAR will enable scientists to gather valuable data about our planet and improve our understanding of its complex systems. As a future mission, NISAR is currently in its development and integration phase. This phase involves the assembly and testing of the spacecraft and its instruments. The teams from NASA and ISRO are working closely together to ensure that all components are integrated seamlessly and function as expected. The mission has passed several key milestones, including the completion of critical design reviews and the delivery of key hardware components. The mission is on track for its planned launch date, which is subject to change based on various factors. The mission status is regularly updated on the websites of NASA and ISRO, providing transparency and keeping the public informed about the progress of the mission. The development and integration phase is a complex process that requires careful coordination and collaboration between the two agencies. The teams are working diligently to address any challenges that arise and ensure that the mission is ready for launch. The mission status is constantly monitored and evaluated to ensure that it stays on schedule and within budget. The successful completion of the development and integration phase will pave the way for the launch and operational phase of the mission, which will provide valuable data about our planet. The mission status is a reflection of the hard work and dedication of the teams from NASA and ISRO, who are committed to making this mission a success. NISAR's core strength lies in its sophisticated sensor complement, featuring two synthetic aperture radars operating at different frequencies, L-band and S-band. This dual-frequency approach is unprecedented for a civilian Earth observation mission and provides a wealth of information about Earth's surface. Provided by NASA, the L-band radar operates at a wavelength of approximately 24 centimeters. This wavelength is particularly effective at penetrating vegetation canopies and dry soils, making it ideal for studying forest structure, ice sheet dynamics, and solid Earth deformation. The L-band radar's ability to penetrate vegetation allows scientists to measure forest biomass and track changes in forest cover over time. Its sensitivity to changes in the Earth's surface makes it valuable for monitoring tectonic plate movements and detecting subtle ground deformation associated with earthquakes and volcanoes. Provided by ISRO, the S-band radar operates at a shorter wavelength of approximately 10 centimeters. This wavelength is more sensitive to moisture content in soil and vegetation, making it valuable for agricultural monitoring, soil moisture mapping, and coastal studies. The S-band radar's sensitivity to moisture allows scientists to monitor crop health, assess water availability, and study coastal processes such as erosion and sedimentation. The combination of L-band and S-band radar data provides a more complete picture of Earth's surface than could be obtained with a single frequency radar. The two frequencies interact differently with various surface features, providing complementary information. For example, while L-band can penetrate vegetation, S-band is more sensitive to the moisture content of that vegetation. By combining the data from both radars, scientists can gain a more detailed understanding of the vegetation's health and condition. The dual-frequency approach also helps to mitigate the effects of atmospheric interference, such as ionospheric effects, which can distort radar signals. The sensor complement of NISAR is a key innovation that will enable scientists to gather unprecedented insights into Earth's dynamic systems. The instrument design of the NISAR mission is a marvel of engineering, representing a significant advancement in spaceborne radar technology. It's crucial to understand that NISAR isn't just carrying one radar, it's carrying two, each with distinct characteristics and purposes. These are the L-band SAR, provided by NASA, and the S-band SAR, provided by ISRO. The intricate design of these instruments is what enables NISAR to gather such detailed and comprehensive data about our planet. Designing instruments for space presents numerous challenges. These instruments must withstand the harsh environment of space, including extreme temperature variations, vacuum conditions, and radiation exposure. They must also be incredibly precise and stable to ensure accurate measurements. In summary, the instrument design of NISAR is a complex and innovative undertaking. The dual-frequency radar system, combined with the sweep SAR technology, represents a significant advancement in spaceborne radar technology. This sophisticated design will enable NISAR to gather unprecedented data about our planet, providing valuable insights into Earth's dynamic systems.